Hi everyone. In this video, we're going to talk about how to use integrals to find the area between a set of curves. Up front, I want to say that if this is a topic you've seen before, I'm going to start asking you to think about it in a very particular way, which is probably different than what you're used to. And that's because the method I'm about to show you is going to introduce us to a lot of important concepts that we'll be needing for the next several weeks. So even if you've seen this topic before, there should still be something new for you here. First off, let's remind ourselves of some really important facts about integrals. For starters, you should have learned at some point that the definite integral of a function can be thought of as what's often called the net area under the graph. I like to use the term net directed area for reasons I'll explain in just a moment. Now, when I say area under the graph, what I really mean is area which is between the graph and the x-axis. But the definite integral doesn't actually provide us with this total area. What it does provide us with is the difference between two areas. More specifically, it's the area above the x-axis, which I've called A1, minus the area below the x-axis, which I've called A2. And that's why I call it net directed area, because actually the area above the x-axis makes a positive contribution to the value of the integral, and the area below the x-axis makes a negative contribution. That's something you should have seen before. You should also remember that the way this area under the curve is actually found is by adding together the areas of thin rectangles, or in other words, by calculating Riemann sums. In fact, it turns out that the symbols we use for integrals are designed to remind you about those rectangles. Let's convince ourselves of that by taking a look at how the rectangles can be related to these symbols f of x and dx. Let's focus just on one of those rectangles. Okay, technically speaking, these rectangles should be infinitesimally thin in order to get the true area under the curve, but I've exaggerated the width of this one just to improve our visibility. Notice that I also used the letter x to designate the position of this rectangle on the x-axis. Now, whichever x value we used to position that rectangle, we know that f of x would represent the corresponding y value on that curve. And that shows us that f of x can actually be thought of as the height of that rectangle. Now, what about dx? It turns out that dx is defined as a small change in x, in case you are ever wondering what dx actually is. A change in x is normally what we would call delta x, but we call it dx instead when the change in x is incredibly small, as it would be for rectangles which are incredibly thin. In other words, dx represents the width of an infinitesimally thin rectangle as suggested by that picture. Putting this together, this means that f of x dx literally can be thought of as height times width. Or in other words, f of x dx is the area of our rectangle. Height times width gives you area. Actually, it's directed area because if our curve were below the x-axis, then f of x would be a negative number, which would cause the rectangle to contribute negatively to the value of our integral. From now on, I'm going to use dA to denote the area associated with a sample rectangle like this. Just like dx denotes a small piece of x, dA denotes a small piece of A, or in other words, a small piece of area. So hopefully that notation feels natural to you. It turns out that the integral symbol itself also has a meaning which is related to these rectangles. In fact, that symbol represents summation, or in other words, the act of adding things together. After all, don't forget that the integral is really computed by adding together a whole bunch of these thin rectangles. Whereas what we were looking at up to this point was just one particular rectangle. Now, let's summarize by putting all of this together. When we see the integral of f of x dx, we've just seen that this really can be thought of as the integral of dA. Like f of x dx is what I just called dA. And the integral of dA is just a fancy way to say add together all the dAs. And that's because the integral represents summation, as I just said a moment ago. Now, theoretically, adding those dAs together really would provide us with the net directed area, which is what we want from the integral after all. But what I want you to take away from all this is how each symbol relates to the rectangles. So just to summarize, f of x is the height, dx is the width, and the integral itself represents summation of all the rectangles across the entire interval between a and b. Right? Keep in mind these rectangles are infinitesimally thin, meaning thinner than anything you could ever possibly imagine. And in practice, that means that every single x value in the interval has an associated rectangle, and every single one of those infinitely many rectangles contributes to the directed area through the process of calculating this integral. Let's put all these ideas into practice through an example. Find the area between these curves from x equals 2 to x equals 5. The first thing I suggest you do with any geometric problem is draw a really good sketch. So graph the curves you've been given and get a good sense of what you're really looking for. When I say between curves, I mean above one curve and below the other. And we're told that we only care about the area which is between the x values of 2 and 5. Now, the method I'm about to show you is something we'll be building on for the next several topics, so I am going to insist that you solve these problems the same way as me, even if you've learned to do this a different way in the past, since getting used to this method now might save you from getting confused in the future. So if you have your own way to do it, please start doing it this way. Now, just like the area under a curve, the area between curves can be found by adding up the areas of a bunch of infinitesimally thin rectangles. I've just drawn one of those rectangles here, and of course this one doesn't appear infinitesimally thin because I exaggerated its width to increase visibility just like I did before. And remember, we can use the letter x to designate the position of this rectangle. Keep in mind there's actually a rectangle associated with every single x value in this interval, and the one I've depicted here is just one example. I'm going to call this my sample rectangle. Now, if we want to add up the areas of all these rectangles, we'd better know how much area each rectangle has. That area is what I called dA, so let's start by figuring out a formula for that. We'll get a formula for dA as our first objective. We know the area of a rectangle is height times width, and note that the formula we'll come up with here is going to depend on x, because the height of our sample rectangle would change depending on which x value we position it upon. So let's think about the height first. We can see that the height is represented by a vertical distance, and a vertical distance can always be thought of as a difference of two y-coordinates, right? The y-coordinate is what tells you the vertical position after all. So the difference of two y-coordinates would tell you how much vertical distance you have. In other words, if we were to take the y-coordinate at the top of our rectangle and subtract the y-coordinate at the bottom, we would have our height. So for starters, we need to know the coordinates of this point at the top of our rectangle. Well, the x-coordinate of that point would just be x, right? That would be the same x value we used for positioning our sample rectangle. So what about the y-coordinate? Since this point lies on the blue curve, the y-coordinate can be found by looking at the formula for this function. That formula tells you that y is equal to x. So the y-coordinate here must be x. We also need the coordinates of this point at the bottom of the rectangle. And we could think of that one in a similar way, where the y-coordinate here is just given by looking at the formula for the green function, since that's a point on the green curve. So when we go back to finding our height, we know that the y-coordinate at the top is x, and the y-coordinate at the bottom is negative x. Subtracting those will give us that vertical distance. And it's important you go top minus bottom just to ensure that you're getting a positive value for your height. Of course, we can always simplify this as 2x. And so going back to our formula for dA, we now know that the height can be expressed as 2x. But what about the width? Well, the width of the rectangle would be an infinitesimally small change in x, and that is what we call dx. So this completes our formula for dA. Remember that dA represents the area of a sample rectangle. So as a final step, we still need to add all of the sample rectangles together to get our total area. Also remember that adding the dAs together is signified by taking the integral. So if we do this, we'll get our total area, which I've called A, right? Add together all the dAs, or in other words, integrate the dA to get your total area. But we still need to include our integration limits. What should those be? Well, if you were to imagine building all these rectangles across the entire region from left to right, the first rectangle you build would be at x equals 2. And the last rectangle you build would be at x equals 5. You want to add up all the rectangles in between those ones, so we use integration limits from 2 to 5 to indicate that. Now, earlier on, we found the formula for dA, so let's incorporate that information into our integral. And at this stage, we've boiled down the problem to an integral which is pretty easy to calculate. Just take an antiderivative and you're home free at this point. So I'll leave it to you to check these remaining details. That's it for the basics of area between curves, so I'll see you in the next video where we'll look at some more complicated examples.